Okay guys, so welcome to video 2 in the acids and alkalis for GCSE. This one deals with reactions of the acids and the bases, acids and alkalis with a variety of things. This is definitely one worth having your periodic table in your notes with you and having a pause of the video on occasion, doing the questions and then coming back and checking your knowledge and understanding, or maybe going through the video once and then coming back through it for a second time. So the first thing that we're going to look at here is that you have to understand, these are just little cutout typed bits at the top of the page or from your specifications. So the first thing you need to understand in 1.8.8 is that acids dissolve in water to produce hydrogen ions. Now this was already discussed in the video number 1 on acids, the introduction to acids and alkalis. You should be well familiar with it. But we'll just run through it very quickly again just to show you that these are all the acids that you should be familiar with. In fact, there's another one that you should also be familiar with, which is this one here at the bottom, which is again a weak acid called methanoic acid. Okay, so those are all the ones you should be familiar with. But the key thing is that every single acid on the left hand side of this produces hydrogen ions or a proton. Okay, what you should remember from the last one are the things like when they produce one hydrogen ion per molecule, they're called monoprotic. And if I just remind you how to spell that, because they produce one proton per molecule. The likes of the sulfuric acid, where we have two, are called diprotic, and obviously then we have our phosphoric acid just here, H3PO4, which would be triprotic. We then have, so those are all strong acids, and you notice the one-way arrow where they will 100% ionize when they're placed in water. In other words, every single molecule will split up into hydrogen ions and the negative ion, whether it's chloride or nitrate or sulfate or phosphate. And then if you look at the three acids illustrated at the bottom with the double-headed arrow, they are all what we refer to as our weak acids. So these three acids that we have down here, which are, if you remember, ethanoic acid is the first one here, moving down to carbonic acid, if you remember, carbon dioxide dissolving in water, to give you that. And then we have our methanoic acid, which is the one at the bottom. So they only give a very small number of hydrogen ions per number of molecules of the acid that you put into water. And those are ones that you would associate with food and drink, etc., and ones that shouldn't do you very much harm. We also have to understand about alkalis, which are dissolved in water to give us the hydroxide ion. And if we look at these, we can see every single one of them, when we dissolve them into water, will give us hydroxide ions. Okay, and they are the first two, sodium hydroxide, just the one I have there with the green dot beside it. Then we have barium hydroxide, which is what we call dibasic. And then our last one is ammonia in water to give you ammonium hydroxide. And if you look at the ammonia, you'll see it is, hopefully you could understand, a weak alkali, and it only gives us very few hydroxides when dissolved in water. So that's what separates acids from alkalis. Acids give hydrogen ions or protons. Alkalis give hydroxide ions, OH minus ions, when dissolved in water. So what happens then when these two things join together? Well, in 1.8.10, you'll notice that you have to understand what goes on in terms of a neutralization reaction, and that is when a hydrogen ion here from an acid reacts with a hydroxide ion here from an alkali, and what do we get? Well, we get H2O, and that's the reason why it's called neutralization, because our acid has joined to our alkali and it has given us a solution which is water, and that has a pH which is neutral. We also get some heat given out in that reaction, so it's exothermic, and again you need to understand that neutralization reactions are indeed exothermic. Now, how do we measure that? And you should do this in class quite simply. Okay, what we do is we take an insulated vessel, okay, nothing very flash, I'm afraid, it's just a polystyrene cup with maybe a lid on it, maybe not even a lid on it, and we have a reaction mixture in that lid, and we add the acid and the alkali together, and what we do is we record the temperature at the beginning of that, and you'll see we've recorded the temperature here. I've called it B degrees Celsius, Okay, if we just highlight that as being B degrees Celsius, I'll just tidy that up a bit because it's a bit untidy. So we call that B degrees Celsius just here. Okay, and that's what it started off at. And then as we mixed the two things in the vessel, we added a certain amount, it says volume of HCl, that's volume of acid, hydrochloric acid added to the alkali. The temperature, if we look at my line here, I'll just do it in purple, the temperature of course rose, and then when the reaction reached its maximum, the temperature then starts to drop away again because all the acid and alkali have reacted in there. And the maximum temperature was, as I've indicated here, A degrees Celsius. So we can see therefore very simply from that just that the reaction between an acid and an alkali is of course an exothermic reaction, so heat is given out. And the delta T, delta means in chemistry and science in fact, the change, and T hopefully you can all work out stands for temperature. So if we have A degrees Celsius minus B degrees Celsius gives us whatever the delta H, the temperature changes. And that's just a very simple, quick and easy little experiment to demonstrate that a neutralization and reaction is indeed, as we said on the previous slide, exothermic and does of course give out heat. Okay, the next thing we need to be able to do is 1.8.12, which is recall that a base is a metal oxide or a metal hydroxide which neutralizes an acid to produce a salt on water. Well, you should know this from Key Stage 3, but when you're writing reactions, very often students will say to me, sir, well, I don't know what a base actually is. Well, you will recognize it very simply as exactly what the examiner has said here. It's a metal oxide or it's a metal hydroxide. So things like, if we just come down to where my purple line is here, copper oxide, magnesium oxide, those are bases. There's many bases that you should be able to recognize. And then our metal hydroxides are also bases. They will react with an acid to give a salt plus water. The difference between a base and an alkali then very simply is that an alkali is just a soluble base, and you would have to go to your solubility tables on the reverse of your periodic table, and that would allow you to work out whether something is a soluble base and therefore an alkali, or is it insoluble and it's just simply referred to as a base. Okay, so the general equation for base plus acid is that we always get a salt and a water, and that gives you a pH of 7, hence it's called a neutralization reaction, okay, which we've referred to over here. RXN, by the way, is my shorthand for reaction. You may see it pop up now and again if you're unsure what it is. And then just how do we recognize acids or bases, sorry. Okay, so there we go, your metal oxides or your metal hydroxides. So bear that in mind for what comes later. Okay, so we're going to have to start writing some equations, I'm afraid, and this will go back to what we did again earlier in the year, and so you should be able to pause the video, practice these yourselves, and then check if you're still able to do them. Right, so the first thing we're going to look at is just, well, what do we see? What actually happens when a metal reacts with an acid is the first one that we're going to look at here, and we're going to look at the reaction specifically between magnesium and zinc. Well, first of all, the metal will disappear, and that's very simply because the product that is formed is, as we've said here, soluble. And when it's with magnesium and zinc, the product will always be colorless. They form what we call colorless salts. You will get hydrogen, okay? And because you get hydrogen, you will see some fizzing, so that's an observation. Okay, you will also get heat. You might say, well, I can't see heat, but it's still an observation. Things that you can touch are observations, and you can feel heat being produced in the bottom of the test tube. Okay, touch, smell, and see are your observations. Okay. Test for the gas I've said here. Well, I hope you all know that a test, the gas is hydrogen, and you test for hydrogen using a lit splint, and you'll get, of course, that squeaky pop. So there we go, that's our generic equation. If you see along the top, metal plus acid gives us metal salt plus hydrogen. Okay, which metal salt it will be will depend on the acid and the metal you begin with. Your observations are that the metal will disappear because the metal salt formed is soluble. That will form a colourless solution because zinc and magnesium salts are colourless. You'll get some fizzing because hydrogen gas is produced in water really, and you'll get heat given off. Okay, and you test for that gas to prove that it is hydrogen by a lit splint to give you a squeaky pop. Right, let's have a look at the equations which we all love to do. So it might be an idea for you now to pause the video, go and do a few of these and come back. Right, so magnesium chloride reacts with HCl, which is hydrochloric acid. Hydrochloric acid, you should all know, it's an acid and it gives us chloride salts, again covered in the second or third topic you do in year 11 when you do reactions of formula and equations. So it gives us the chloride, which will of course be magnesium chloride, MgCl, and we always get hydrogen with it. Now we must check our formulas because Mg is in group 2 and is plus 2, chloride is in group 7 is minus 1, so it's MgCl2, which means we need to go back and get enough hydrogens and chlorines on the left, and then we need a 2 on the left. Magnesium with nitric acid gives us magnesium. Nitric acid always gives us nitrates, and a nitrate is an NO3. Magnesium is 2 plus, nitrate is 1 minus, so we need 2 nitrates to balance out the 2 plus. Remember, it's a nitrate, it's polyatomic, so we're going to need 2 of them. It's an acid plus a metal. We always get hydrogen and it's diatomic, in other words it's H2, so we need to go back and get our 2 hydrogens and our 2 nitrates, and that's how we do it. Magnesium with sulfuric acid, well this time we get a sulfate, okay, which is magnesium sulfate of course, MgSO4, and we get hydrogen gas as we always do with a metal and an acid, and that one self-balances very kindly, so that makes life a little bit easier for us. Magnesium, just write it on there, is of course 2 plus, and sulfate is 2 minus, so the numbers cancel. Then we have a look at the zinc ones, and to be honest with you guys, if you remember, zinc is a 2 plus ion, as is magnesium, so the reactions, the equations are identical except you swap in magnesium this time for your zinc. So we go ZnCl2 plus H2, go back across and get your 2 hydrogens and your 2 chlorines. We have Zn nitrate, zinc nitrate, which is as so, of course, plus your 2 hydrogens. Go back and get your 2 hydrogens and your 2 nitrates, and the nice simple one at the end, which is the zinc sulfate plus the hydrogen. No balancing required, probably worth 1 mark less at GCSE. So those are all your equations. You need to be able to write them all. I've only written the balanced symbol equations there. I haven't bothered with word equations. I'm assuming that word equations are well beyond you now, and you can do those very easy. So that's your general reactions of metals with an acid. And we'll have a look at a metal with an acid here before we go any further. We'll have a look at some magnesium reacting with zinc, and hopefully you'll see all the observations that I spoke about. You probably won't see heat, but you should see the fizzing, the metal dissolving, the soluble salt. So let's have a look at this. So the last bit of magnesium left there, it fizzed away, dissolved, colourless solution. Heat would be produced if there was a thermometer in there. We'll have a look. I think I've got zinc on here as well. Do indeed, and let's have a look at the zinc. Should be a little bit less vigorous zinc. It's not quite as reactive as our magnesium. So you can see the fizzing, see the bubbles coming off. It's nowhere near as vigorous. Take quite a long time for all that piece of zinc to disappear and form our colourless solution. But you get the picture. Okay, so let's have a look next at acid plus alkali. This is a fairly uninspiring reaction. Acid plus alkali gives us salt plus water plus a bit of heat. Okay, and we already looked earlier at how we would follow this reaction in terms of practical. We really just get a colourless solution, nothing particularly exciting about it. We can have a look at it here. This one is tracked with phenolphthalein indicator. Okay, so you can see yourself, there's no fizzing, because there's clearly, of course, as you can see from the equation up above, there's no gas given off, no gas produced. This is exactly the same reaction here, but with a different indicator. And I would hope that you're all able to work out what indicator that is. It was, of course, universal indicator, and you were adding acid from the burette to alkali, which was in the beaker, and it slowly turned acidic from alkali, hence going from that sort of dark purple through sort of green, yellow, down to the red. Okay, so we have got some reactions to write here of acids reacting with various different alkalis, sodium hydroxide, potassium hydroxide and calcium hydroxide. So again, I'll write the equations. You may well want to pause the video, do them yourself, and then come back and check. Okay, so we have sodium hydroxide and hydrochloric acid. We will get hydrochloric acid gives us chloride, and of course it will be a metal salt, sodium chloride, and we always get water. Okay, that equation requires no balancing. If you count everything up, you'll see everything's in place. Nitric acid gives us a nitrate, sodium nitrate of course, and again we need water, and that is another one which very kindly balances itself out. And sulfuric acid is sodium sulfate. Remember, sodium is +1. I'll just pop that on. Sulfate is -2, so we need a little 2 there. And we also get, as we do every time, water. That one will not balance itself out, and we need 2 NaOHs, okay, and that will give us 4 hydrogens on the left, so we need to double our hydrogens up on the right. Potassium hydroxide then gives us potassium chloride, which is KCl. Potassium is 1+, chloride is 1-, so it is of course just KCl. And we need 1 water. Potassium nitrate is KNO3, and again we just need 1 water, and that self balances. And hopefully you've cottoned on now. Just put in our 1+ and our 1- there to remind you that KSO4 is K2SO4. We need 2 waters because it's the same valencies as the sodium sulfate up above, and we would need 2 KOHs if we were asked to balance that in an equation. Okay, then we're going to move on to calcium hydroxide, which is a little bit more complicated, I suppose, in that calcium itself is 2+ and hydroxides are 1-. And that goes to calcium, which is again, remember, 2+, and chloride, calcium chloride, because it's hydrochloric acid, is 1-, so we need CaCl2, and of course we need, as we always get whenever we react an acid with an alkali, we need water. And if we go back and we do our balancing, we'll find that we need some numbers as so to get everything balanced up. Right, calcium hydroxide and nitric acid will follow the same pattern, except we would need brackets because a nitrate is polyatomic, and we will need water there. We will have to go back and get our 2 nitrates there, and that will mean we would need 2 waters there. Calcium sulfate is a bit easier because calcium is 2+, and our sulfate, as you will know by now, is 2-, so it's just 1-to-1 ratio, and again it's acid plus alkali, so we do of course always need our water. If we just pop our calcium hydroxide in on the left hand side here, you'll see I have 4 hydrogens on the left, and I therefore of course need 4 hydrogens on the right, and I get those by two water molecules. So those are all your reactions that you need to be able to write. Your observations are up above. They're nothing very dramatic with those. You saw the videos. We're going to move on now to the reactions of a base, an insoluble base this time, with an acid. So we're going to look at copper oxide, and I don't think I have magnesium oxide, but it's a similar sort of idea. The only difference is that with the salt in magnesium oxide it's colorless, whereas the salt in copper oxide is a blue color, and you'll see that in a second. So the key thing here is that the base being, both these are insoluble, so in other words your observation would be that your solid would dissolve during the reaction, and you get a little bit of heat given off as well. Okay, copper oxide is a black solid, and you need to note that to the examiner, that the black solid changes color, and whenever we do with hydrochloric acid, it goes to, again you can pause the video and write these equations and come back and check them if you like. It goes to copper chloride, and copper is 2 plus, chloride is 1 minus, so it's CuCl2. It's always salt plus water, so of course we'll always pop our water in. We need to balance, so we'll go back and do that. Copper chloride is a green solution, greeny blue, okay, really, I suppose. So green dash blue or green hyphen blue. Okay, so you'll have a black solid dissolving to a green blue solution on a bit of heat. Copper nitrate is the same color really as copper chloride, but again we need to bracket our nitrate. Okay, we'll always get water of course, and we need to go back and we need to get our two nitrates from there, okay, and balance up our water as well. Copper sulfate is CuSO4. Okay, copper is 2 plus, sulfate is 2 minus, so they react in a 1-to-1. This is much more of a blue solution than a blue-green solution, unlike the top two. And again, of course, we have our H2O. That one very kindly self-balances. If we look then at our magnesium is a white solid this time if we're talking about our observations to the examiner, and it goes to magnesium, which is 2 plus, and chloride, which is -1. And again, of course, we get water. Magnesium chloride is a colorless, all magnesium salts are colorless, and I write SOLU short for solution. And remember, we go back, we need 2 hydrogens for the water and 2 Cls for the chlorides. It's getting a bit untidy here, but we'll sort of go down, draw a line, we'll go below this. Okay, we'll come down here. Okay, so we've got magnesium nitrate, MgNO3. Again, magnesium is 2 plus, nitrate is only -1. And of course, we always need our water for an acid plus base. So we go back and balance that. Magnesium sulfate is Mg, 2 plus, sulfate is 2 minus, plus we need our water there as well. Okay, so the magnesium chloride, the magnesium nitrate, and the magnesium sulfate, guys, they're all soluble, and they will all give you colorless solutions, whereas the copper salts go from black solids to colored solutions, all of which are on the board. Okay, so I think we have covered everything there. We'll have a look at the video here of copper oxide reacting with I think it's with hydrochloric acid, so you can see the sort of the blueness of the solution, you can see the black of the original copper oxide, and you can see what sort of happens to this as it goes through the reaction. So that's just this black solid copper oxide put in. That's the reaction being heated and turning into copper sulfate, which was, I'll just bring that back a little bit. Okay, so that's the start formation of the blue solution of the copper chloride. I'm going to filter out the unreacted copper oxide here to get rid of it, and you'll see the blue solution collecting of the copper sulfate, down at the bottom. So that's, I'll just come back to that. So that's the blue solution at the bottom there is copper sulfate, so the acid here is sulfuric acid. The black substance in the filter paper is unreacted or excess copper oxide. You can see it well there now. And then we're just evaporating off any excess water from our copper sulfate to try and get some nice crystals. If we leave them then for a few days and you let the water slowly evaporate off, you get some nice crystals starting to form there. You can see them on the screen. I'll just reduce that down a little bit, might make it a little bit clearer for you, of copper sulfate. Okay, so again, that's everything that you would be expected to know, your observations that you'd be expected to see. Right, another reaction then of acids or metal carbonate, and there's plenty to see in this one. So the first thing is that the metal carbonate, if it's a solid, it will dissolve. And I've said if it's a solid, so read the question and see does the examiner tell you it's a solution of the carbonate. If you write it dissolves at that point, you will not get any marks. Plus the acid to give you a metal salt, which is probably soluble and is usually colourless, but it may be coloured if you start off with a transition metal compound over here as your metal carbonate. So for example, copper carbonate, that would give you with an acid, the same colour of salt as we got on the previous slide with our copper compounds. Okay, you'll get fizzing here because you have carbon dioxide being produced, and you'll get some heat because it's an exothermic reaction. Okay, how do you test for the gas? Well, it's carbon dioxide gas. You'll be looking for the lime water test, which you should all be very familiar with, and you bubble the gas through lime water, and of course, hopefully you all know that will turn milky. That's your positive test for CO2, carbon dioxide. It'll also extinguish a lit splint, but I don't like that one particularly well. I much prefer the lime water turning milky test, and I suspect examiners would too. Right, so I'm going to write these equations again. You can pretty much for all of them put in straight away water. Not pretty much, you can put in water and carbon dioxide for every single one. You just have to work out the name and, more importantly, the salt formula. So we've got calcium, which is, remember, a +2, and chloride is a +1, so that's our -1, so we've got CaCl2, we need a 2 there. We have calcium nitrate, calcium is +2, nitrate is, of course, you'll know well by now, -1, so we need 2 of those, and we need to go back, pop our 2 in there. Calcium is +2, sulfate is -2, so that is all good. That one will self-balance. Copper chloride then, so all of these salts, all these calcium salts that we've made here are all colourless salts. This reaction here is a bit of an odd one because it will go sort of quickly enough at the start, but it will stop very quickly. The reason for that is because calcium sulfate is insoluble, and it basically coats the reacting compound and halts the reaction really quite quickly. Okay. All the other salts here are aqueous, and they just form white solutions, or sorry, colourless solutions, not white. Okay. Copper carbonate then is a green solid. So what happens? The colours of these salts are the same as copper chloride, copper nitrate, and copper sulfate from the previous slide. Okay, so we have CuCl2. Okay, I'm not doing the balancing of the formulas because this was done on the previous side, of course, plus water and carbon dioxide. Okay, we need to balance. We have copper nitrate, which if you remember from the previous slide is the same as copper chloride. It's that sort of greeny blue colour. And if we look at copper sulfate, sorry, I need to balance that. Copper sulfate, we'll just scroll down here a bit. Copper sulfate is CuSO4. It's more of a blue than a bluey green. It was the one we saw in the video. That equation rather kindly self-balances. Then we've got hydrogen carbonate, and it's the same general equation in that we get a metal salt plus water plus carbon dioxide. Always think carbonate and hydrogen carbonate gives us carbon dioxide. Sodium chloride is, sodium is +1, chloride is -1, NaCl plus water plus CO2. Sodium chloride is a colorless solution, is what you would make there. Okay. Sodium nitrate is Na plus 1, nitrate is NO3, K is minus 1, so they cancel each other out. And we get that. Then we have sodium sulfate, Na is plus 1, sulfate, remember, is minus 2, so we need 2 sodiums plus water plus my carbon dioxide, of course, and I'll just go back over here because I need 2 NaHCO3, and in that one again we will get 2 of our waters, and we will get 2 of our carbon dioxides. So there's a little bit more work involved in balancing that particular equation. So those guys, I think I have a video there of a carbonate reacting with an acid, which I can show you just before. Okay, so if we look at our solid, this is a solid carbonate this time, reacting with acid. Okay, so you can pretty much see the colourless solution forming. You can see the solids starting to disappear. They haven't added enough acid for it to completely disappear. You definitely heard the fizzing. We'll just run it again. You can see the bubbles there. Okay, so all the observations really that I spoke about. Okay, a bit more acid would have made it clearer for us. Okay, then we have our acid with ammonia, and this is a fairly undistinctive reaction. You don't see very much at all. The only thing that you can get here is if ammonia has a rather pungent smell, which I've said here, and because it turns from ammonia into an ammonium salt, that smell disappears. Now, a lot of time people will get the ammonia and the ammonium mixed up. Ammonia is NH3, which we have in the equations here, and ammonium ion is NH4 with the +1 charge. So please be careful, guys, whenever you're doing that you don't get those two mixed up. The other thing about this equation is it's a bit of a special case, as I've said here, in that ammonia plus an acid only gives you an ammonium salt, and this time you do not get any water, you do not get any carbon dioxide, nothing else produced. So ammonium with hydrochloric acid is an ammonium chloride, NH4 is the ammonium, chloride is Cl, the ammonium is, remember, 1 plus and that's 1 minus, so they cancel each other out. Ammonium nitrate, NH4 is +1, nitrate is NO3, and then the one that's a little bit more challenging but not too bad is ammonium. We need 2 of those because sulfate, remember, is a -2 and ammonium is simply a +2. But there's no water, don't put water in because you'll never get it balanced. Okay, we've done that. We've done the tests, okay, for carbon dioxide, and we've done the test for hydrogen both. You should have been familiar with those even before. Okay, so we spoke a lot about salts, but you need to know exactly what salt is, and it's defined as whenever the hydrogen ion, if you look at green up there, the hydrogen ion of a salt is replaced by a metal ion, and you must say replaced by a metal ion. If you leave out the word ion and you just write by a metal, you won't get the marks here. And we just look at a few salts and see if we can kind of see why they are, as I've said. So there's hydrochloric acid, and there's the hydrogen ion, the arrow going to it, in hydrochloric acid. After the reaction we've made sodium chloride, we now have a metal ion. That is a sodium +1 ion in there. We don't write the charge on, okay? But our hydrogen ion has been replaced by a metal ion, a sodium ion. The same is true here in nitric acid. My hydrogen ion has been replaced by a sodium +1 ion. We now have a salt. Sulfuric acid, the same again. I have 2 hydrogen ions in sulfuric acid. In this particular reaction, they have been replaced by potassium K+ ions. That makes it a salt. Okay, down below then we have magnesium oxide with hydrochloric acid. Again, my hydrogen ion and my hydrochloric acid it has been replaced by a magnesium or a metal ion, so therefore that is a salt. And that's our definition of salt. You need to know all your definitions. They're at the start of each of your set of notes. Right, next you need to know some colours. Metal, first one there is copper oxide. It's an insoluble black solid, okay, and you should know that anyway. We already covered it earlier in this video, yeah. The next one that we need to be able to describe is copper carbonate, which is a green, very beautiful green solid, okay. Very rarely see it as that, more likely to see it like this, where it's a green powder is what you'll be presented with in class, okay. This is its naturally occurring form on the right hand side. When it's dug up out of the rock, you don't get quite such a pretty or expensive example of it, I'm afraid. And then we have what we call hydrated copper sulfate, and hydrated copper sulfate are these very pretty blue crystals that you will see, and down below it there we have a solution of copper sulfate, okay. Hydrated just means that it has got water attached in the crystal. It would have a formula of CuSO4, and you'll know something's hydrated. It'll have a dot and then some water after the dot, which represents water of crystallization, okay. So it's water trapped in the crystals. If I was to heat that, I would get rid of the water, and that would become a compound called anhydrous copper sulfate. And it's very different looking. It's a white powder as opposed to that nice blue crystal that you see in front of you there now. Okay, and that, guys, really covers pretty much all of the topic of the reactions of acids. I'll just put those substances back on the screen there for you to have a look at if you want to remind yourself what they look like. Okay, so hopefully that helps you with your acid-base reactions and observations and equation writing. 2 videos there which you should hopefully rely on quite heavily during revision time.